Let's look at question number 1. How far was the lightning if it took 12 seconds for the sound of thunder to reach you? Well, our time was 12 seconds. Our velocity of sound now, is equal to 343 meters per second. We simply use velocity equals distance over time. Rearrange it. You have 343 meters per second times 12 seconds, and you land up with an answer of 4,116 meters. So that's how far the lightning was when it struck. If you change that to miles, it's just 2.6 miles. You don't have to do it. I just wanted to show you. The second question is based on the first question. If you know that the storm is 4,116 meters away, how long did it take the light to get to you? So you use velocity equal to distance over time again. In this case, you're going to use the velocity of light, or v sub c. Here it is, 4,116 meters divided by 3.0 times 10 to the 8th meters per second. And you land up with an answer of 1.4 times 10 to the negative 5th seconds. So that's how long it takes for lightning to reach you. If the storm is 4,116 meters away, it's about 2 miles. New question, question number 3 says, if it only takes half a second for the thunder to reach you once you see the lightning, our velocity is 343 meters per second. Again, we're talking about sound, not light here. It takes 0.5 seconds for the thunder to reach you. You use velocity equals distance over time. Here it is rearranged, 343 times 0.5 seconds. The storm is 172 meters away in this case. Question number 4 is based on 3. If the storm is 172 meters away, and we know the velocity of light is 3 times 10 to the 8th meters per second, can we figure out how long it will take the light to reach us? And in this case, the light reaches us much quicker than in question number 2. We have 5.7 times 10 to the negative 7 seconds. That's how quick it takes the lightning to reach you. Question number 5. There's a firework. It takes 3 seconds for you to hear the sound afterwards. How far is the firework from you? The time is 3 seconds. The velocity is 343. Just plug it into the formula, and you land up with the firework explosion being 1,029 meters away. Question number 6. How long does it take the light to reach you? Again, it does take light time to reach you. In this case, the velocity is 3 times 10 to the 8th meters per second. We know the distance from above is 1029. We plug it in and we say that the light reaches us in about 3.4 times 10 to the negative 6 seconds. Problem number 7. One of our closest stars is located 4.11 times 10 to the 13th miles from Earth. How long does it take for the light to reach us in years? Well, we simply use the velocity equals distance over time. Rearranged it. Time is equal to distance over velocity. What is the distance? 4.11 times 10 to the 13th miles. And it is always, we can't use miles, so we just rearrange it knowing what we know. Put it into the formula, and it takes 2.2 times 10 to the 8th seconds to reach us. Question number 8. If sound could travel through space, how long would it take for the sound to reach us in years? Well, velocity of sound is 343. The distance is 4.11 times 10 to the 13th miles, or 6.6 times 10 to the 16th meters. We do have to put it in meters. We can't use miles. We simply use time is equal to distance over velocity, and we land up 1.9 times 10 to the 14th seconds. Again, that doesn't make a whole lot of sense to us. So let's convert seconds to years. Here's the way we do it, like we did a while ago, and it takes 6 million years. So if you yelled out, "Hello, star," it would take 6 million years for that sound to reach the other star. This slide tells us how to solve problems 9 through 15. These are the doppler effect formulas. We have 2 of them. In one case, this formula is used if there's a moving source of sound or a moving source of light. An example would be a train coming towards you with its siren on, or a spaceship coming towards you with its lights on. The second formula is for a moving observer. What do you mean by that? That means if you are traveling towards a train with its siren on, or you are traveling towards a star that's shining its light. You are moving, you are the observer, you are not emitting the sound. What you have to be careful with these formulas here is looking at this positive and negative. There's two different ways to interpret this. If it's a moving source and if it's moving away from you, in this case, this is a positive sign. If it's a moving source and it's moving away from you, make sure you take this as a negative sign. The opposite is true for a moving observer. So if you are moving towards a light source or you are moving towards a siren, this becomes positive if you're moving towards the object, and if you're moving away from the object, you make sure this is negative. These can be found on page 508 and on 510. In problem number 9, you are tossing a frisbee around with some friends, and some joker on a mini bike races across the field directly towards you, blasting Adele's Hello. From your experience of hearing the song, you recall that Adele, about 15 seconds into the song, hits a high note of 262 hertz. But you definitely hear it at a higher pitch. You think, man, she sounds out of tune. She's singing at like 278. Of course, this is being kind of funny that you can tell the difference, but you really can. Number 9, how fast was the person traveling on the mini bike? Now, the Doppler effects allow you to solve this problem. First of all, what do we know? We know the velocity of the source? No, we're asking, what is the velocity of the source? What is the velocity of the mini bike? The frequency of the source, we said that Adele's voice is singing at 262 hertz. We know that it's on the bike, it's 262. That's what it's supposed to be. That's what it is when it's coming off the bike itself. Now you hear the frequency at 278. Using this formula here, you should be able to find how fast that mini bike is going. So do you have the frequency of the observer? Yes, 278. Do you have the frequency of the source? Yes, 262. Do you have the velocity of the source? No, that's what you're looking for. Do you have the velocity of sound? It's always 343 meters per second. I rearranged this formula here. A velocity source is equal to 1 minus velocity source over frequency source over frequency observer times the velocity of sound. On the next slide, I'll show you how to rearrange that. So let's see how this is rearranged. Velocity source is equal to 1 minus frequency of the source is 262. Frequency of the observer is 278 times velocity of sound, 343. Your answer is 20 meters per second. So the mini bike was going probably about 45 miles per hour.